Hello everyone, welcome back to my YouTube channel. Today we are going to study about nucleophilic substitution reactions of haloalkane. Halo is a short form of halogen, right? And alkane, we know that it is an hydrocarbon which contains carbon-carbon single bond. Okay? So, haloalkane means in that carbon-carbon single bond, one hydrogen atom will be replaced by an halogen group. One or more hydrogen atoms in hydrocarbon will be replaced by the halogen. See, what are the halogens? Fluorine, chlorine, bromine, iodine. It goes like that. See, I will show you one hydrocarbon. Can you give me a simple hydrocarbon? Methane. Methane is CH4. See, the replacement of one or more hydrogen atoms by a halogen group, it is known as haloalkanes. See, I am replacing this hydrogen atom by any of these halogens. For example, if I take chlorine, it will be like HCH. So what is formed now? An haloalkane is formed. We call it as chloromethane or methyl chloride. Now what is haloarenes? See, can you give me an example of an aromatic hydrocarbon? Yes, benzene. So this is replaced by, the hydrogen atoms in benzene is replaced by a halogen, right? So one or more hydrogen atoms will be replaced by a halo group, right? So this is known as chlorobenzene, right? So this is a haloarene. The general representation of haloalkanes is, so this can be denoted as C, okay? And this can be denoted as X, because X is a halogen group. So X can be fluorine, chlorine, bromine, iodine, etc. The CX bond on this haloalkane is a polar bond. That means the carbon carries a partial positive charge and the halogen carries a partial negative charge. So the carbon atom of this haloalkane, the positive charge on the carbon atom of this haloalkane makes it susceptible to be attacked by nucleophile. So nucleophile comes in attack on this carbon. Why? Because carbon is carrying a partial positive charge. And one more thing is that this nucleophile is more stronger than this halide ion. Then only it can come and attack on this carbon atom. Now what is a nucleophile? Nucleophile can either be negatively charged species or they can be neutral molecules which carries a lone pair of electrons. So negatively charged species means, for example, OH minus, Cn minus, RO minus, that is alkoxide ion, or RCO minus, that is carboxyl electrons. Nucleophile that is more stronger than a halide ion comes and attack on the carbon atom of this haloalkane. So when it attacks, it forms a new bond with carbon. This nucleophile makes a new bond with carbon and this CX bond breaks. And this X will be displaced along with its electron pair. See, CX bond reacts with nucleophile. So what happens? The nucleophile attacks on this carbon atom which is carrying a partial positive charge. This is partial negative charge. So it comes and attack on this carbon and forms a new bond. So when it comes and attack and forms a new bond, this bond will be broken. That is, CX bond will break and it gets the shared pair of electrons and get displaced along with this shared pair. So the new bond formed is C and U. Okay, carbon and nucleophile plus this X will be displaced along with its electron pair. This halide ion is displaced with this electron pair, and this halide ion which is displaced, we call it as leaving groups. With halides, iodide ions are better leaving groups than fluoride, chloride, bromide. So the reactivity of alkyl halides towards nucleophilic substitution goes like this: Ri greater than RBr greater than RCl greater than Rf. That is, to break Ri bond, there is only low enthalpy is required, or low energy is required to break Ri bond. So Ri is more reactive than RBr. R represents the alkyl group. Okay, RCl greater than Rf. Let's see some examples of nucleophilic substitution reactions. CH3X plus NaOH. So OH is the nucleophile here. So the leaving group is X. So how will the reaction take place? Like this. CH3 will combine with OH. So it becomes CH3OH plus NaX. Let's see another example. CH3X plus sodium iodide. See here CH3I, right? CH3I plus Na plus. The leaving group is X. The nucleophilic substitution reactions of alkyl halides is found to proceed in two types of mechanisms. That is substitution nucleophilic bimolecular, that is known as SN2, and SN1 mechanism, that is substitution nucleophilic unimolecular. First one is SN2 mechanism. Now in this we take an example of methyl bromide, CH3Br plus OH minus, that is a nucleophile. So what is happening here? This is the leaving group. Br is the leaving group, so it gets OH will get attached with CH3 and forms CH3 OH plus Br minus. Now in SN2 mechanism, why it is known as SN2? That is, it follows second order kinetics. That we have studied in chemical kinetics chapter. That is, the rate depends on the concentration of both the reactants. That's why it follows second order kinetics. So how will you write the rate? Rate is K into, K is the constant, K into concentration of CH3Br and concentration of OH minus. So what will be the order of this kind? Order will be 2. Okay, so this is known as, it follows first order kinetics. Generally we represent this reaction as R equals K into CH3X, right? Br will write it as X, and this is nuclear. In this mechanism, the OH minus, that is a nucleophile, attacks the carbon positively charged, that is partially positively charged carbon atom of this haloalkane from the back side. Now when OH minus attacks this carbon, it is trying to form a bond with carbon. At that time, this CBr bond will break. Okay. Now it forms a transition state. In transition state, the carbon is simultaneously bonded to the incoming nucleophile. That is, nucleophile is coming over here. The incoming nucleophile and also the outgoing leaving group. We know that Br is the leaving group. So that is a transition state. And as we know, carbon is bonded to 5 other atoms here. 1, 2, 3, 4, 5. Since carbon has only 4 valencies, it gets bonded to 4 atoms only, 4 other atoms. But here carbon is bonded to 5 atoms and it forms a transition state. Now this bond exists, that is, it's not stable. The structures are not stable. So what happens? Here comes the leaving group, that is Br minus, and here it forms the alcohol. So here it is CH3OH, that is methanol. And this Br minus is the leaving group. As this happens, the configuration of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind, and that pushes away the leaving group. This configuration we call it as inversion of configuration. Now let's see the reactivity of alkyl halides towards SN2 mechanism. That is, methyl halide is more greater than primary halide, greater than secondary halide, greater than tertiary halide. So methyl halide, that is CH3X, greater than CH3, CH2X, greater than secondary halide CH3, CH, CH3X, greater than C, CH3, C, CH3, CH3X. So how will you know that is a primary halide? That is a halogen which is attached to the carbon atom is attached to only one carbon atom. So that's why it is known as primary halide. Secondary halide means the halogen which is attached to the carbon atom is attached to two other carbon atoms. Tertiary halide means the halogen which is attached to the carbon atom is attached to three other carbon atoms. Now see, tertiary halide is least reactive towards SN2. Why? This is because of the presence of bulky groups near this carbon atom, and that hinders the attack of nucleophile. The nucleophile comes in attack on this tertiary halide. The presence of these bulky groups then hinders the reaction, and the hindrance we call it as steric hindrance. So because of the steric hindrance, that slows down the reaction. So in this, which one has the maximum steric hindrance? Here, right? Tertiary alkyl halide have the maximum steric hindrance because of the three bulky groups. Whereas in methyl halide, there is only one methyl group. So there is least steric hindrance here. Whereas here there are three methyl groups, there is maximum steric hindrance in tertiary halides. That's why tertiary halides is least reactive towards SN2 mechanism. Next is nucleophilic substitution reaction unimolecular. That is SN1 mechanism. Now in SN1 mechanism, we are taking tertiary butyl halide, that is tertiary butyl bromide here. So that reacts with OH minus, that is nucleophile, and it forms tertiary butyl alcohol and bromide ion. Now this follows SN1 reaction follows first order kinetics because the rate depends on the concentration of only one reactant. So how will you write the rate? Rate equals K into concentration of CH3 thrice CBr. Rate depends on the concentration of only one reactant. So it follows first order kinetics. This follows first order kinetics. So how will you write the general reaction here? General way. Rate. So the general representation is rate equals K into concentration of Rx. SN1 reaction takes place in two steps. First step is formation of a carbocation. See, we have taken tertiary butyl bromide. So this is a slow step. That slow step is a rate determining step. We studied in kinetics. Slow step is a rate determining step. The polarized CBr bond, that is partially positive charge and partial negative charge. The polarized CBr bond undergoes a slow cleavage to form a carbocation and a leaving group. The next step is step number 2, that is nucleophilic attack on this carbocation. Now see, carbocation is a very reactive species. So it reacts readily with OH minus to form tertiary butyl alcohol. So this is a fast step. The other one was a slow step and that one was a rate determining step. Now this one is a fast step and tertiary butyl alcohol is formed. Order of reactivity in SN1 mechanism. Here we have taken tertiary halide. Tertiary halide is more reactive than secondary halide, than primary halide, than methyl halide. Why tertiary halide is more reactive towards SN1 mechanism? This is because of the carbocation. That is, tertiary carbocation is more stable than secondary or primary or methyl. Now let's see the differences between SN1 and SN2 mechanism. See, first you have to define what is SN1. That is one difference. It is a unimolecular nucleophilic substitution reaction. Here it is a bimolecular nucleophilic substitution reaction. So first difference is over. Second one, what does the rate depends on? Rate depends only on the concentration of haloalkanes in the case of SN1. That's why it follows first order kinetics. Where? Now second SN2 mechanism, rate depends on the concentration of both haloalkanes and nucleophile. So it follows second order kinetics. Fourth one is it takes place in two steps. SN1 reaction takes place in two steps, whereas SN2 takes place in a single step. Now while it takes place in two steps, a carbocation is formed, right? And here there is no carbocation formed. In SN1 reaction, it is favored by polar solvents, and in SN2 mechanism, it is favored by non-polar solvents. The order of reactivity. In SN1, remember like this, if you are taking 1, it will be 3, okay? Tertiary halide greater than secondary halide, then primary halide, and then methyl. And here it will be like methyl greater than primary, greater than secondary, greater than tertiary. So remember like this, for SN1, you take tertiary, okay? For SN2, you take methyl, okay?